Yeah, I accept it.
All right. So, as I said, we have a great guest today giving our the talks for our series. Is Juan Calderón Bustillo. Juan has done his PhD in gravitational waves, starting his career in 2012, joining the LIGO scientific collaboration, interpreting signals from intermediate mass black holes. So he did this at the Universidad de Islas Baleares, and then after his PhD in 2015, he then held 2 postdoctoral positions at Georgia Tech, the United States, and in Australia, in the Monash University, and then was a research assistant professor at the Chinese University of Hong Kong until October 2020, which were quite interesting times to be around there. Since then, he has been working as a Marie Curie Fellow and holding a La Caixa Junior Leader Fellowship at the IGFAE, at the Instituto Gallego de Físicas de Altas Energías in Santiago, and now has done some fantastic work interpreting the signals of the most recent gravitational wave events, and he's going to talk to us all about it. So thank you very much, Juan, for joining us this morning, and after the talk, we'll have some time for questions as usual. So thanks.
Okay. Thank you very much. Thank you for the very nice introduction, and also for the invitation to present this work at a particle physics group, which is actually I think it's the first time I get to do such a thing with this piece of work. So yeah, what I want to talk about today is a bit of an introduction to gravitational waves and what we've been doing with them to date, especially within the LIGO scientific collaboration. And I want to focus on one of our detections. We have 50 right now, but one of them is very, very special. And it offers ways to alternative interpretations other than the typical interpretation we give to gravitational waves, which is the collision of 2 black holes that at the end form another black hole. So I will try to focus on that. So the title of this, the weird title that this talk has towards the gravitational wave catalog of Proca-star mergers, is almost equivalent, as you will say, to the question of have LIGO and Virgo detected dark matter. So that's the answer. That's the question I'm going to try to answer throughout the talk. But first of all, let's do a rather short introduction to gravitational waves, to the LIGO and Virgo detectors, and what current detections of gravitational waves look like, and what we've learned, or a bit of what we've learned from them so far. So of course, one has to start from the very basics, which is describing a bit what gravity is about. As you all know, gravity, since the beginning of the 20th century, is not anymore considered to be a force. It's rather just the consequence of the curvature of space-time, which makes masses in it follow its geodesics, or its shortest paths. So such geometry is, of course, determined by the matter and energy that we place in space, and the geometry this matter and energy creates determines the trajectories on that space. So, of course, this is the same as saying space-time tells matter how to move, and matter tells the space-time how to curve. So once you get to this picture of gravity and space-time, it's rather natural. It took Einstein about a year to get to the conclusion that if you start to move those distributions of matter around in certain ways, you will create a disturbance in space-time that will propagate away from the source, and that far away from the source is going to behave like a wave. So this is what we call gravitational waves. These gravitational waves are going to travel at the speed of light. This is not an imposition of the theory, it's a consequence. Of course, they carry information about their sources, and that's why they have astrophysical interest. If we detect these waves, we're going to be able to study the processes that produce these waves, and that in most of the cases do not produce light. So these things are unique. And anything can essentially produce gravitational waves. I can do them if I move my hand. But creating a decent gravitational wave that we can detect requires extremely violent astrophysical events, because space-time, roughly speaking, is extremely rigid. So in order to disturb it, you need a lot of energy to be released in a short amount of time. So what kinds of sources can produce these gravitational waves that we know that they may exist and that we may have a chance to detect? So there is a whole family of sources, and for each of these sources that emit in a given frequency range, there is a kind of optimal detector to try to detect them. So the most obvious sources one can think of is, of course, the Big Bang. This is the most violent thing that one can think of, I guess. We have supernovae, the explosions that stars undergo when they are about to die, and then in most of the cases they leave black holes behind. And of course, these black holes, when they form, they can eventually form couples, start to orbit each other as they emit gravitational waves and eventually collide, producing a strong burst of gravitational waves that we can detect. The frequencies of this emission are typically within the range of 10 to 1000 hertz. And these are particularly well suited to be detected with Earth-based detectors that we have now, as the Advanced LIGO detectors in the US. The one I'm surrounding here is the one in in the state of Washington, in Hanford, and the one at the top is the one we have in the state of Louisiana, in Livingston. If we want to detect gravitational waves of lower frequencies, such as those produced by collisions of even more massive black holes, namely supermassive black holes, we need to get access to lower frequency ranges we cannot do in the Earth because of the seismic noise of the Earth. So we have the plan to send a detector to space, namely LISA, which is planned to be sent by 2034, more or less. These things always get delayed at the end. So let me show how a black hole collision looks like in a kind of movie way. So this is what you would see if you were really close to a couple of black holes and you see them orbit. They start to orbit, they lose gravitational waves, and therefore the orbit is going to get closer and closer and faster, and eventually you're left over with a remnant black hole that is going to emit a very characteristic gravitational wave emission that I will talk about later. So here is the space-time vision of this. So you're observing the curvature of space-time in 2 dimensions. So you can see that right when the 2 black holes collide, the emission is going to be more powerful. It's going to be more clear later. And anyway, these waves get emitted from the source. They travel across the space with nothing basically stopping them. They can suffer lensing or stuff like that, but essentially nothing can stop them until they reach Earth at some point, and they cause a disturbance, which consists on squeezing and stretching space-time in orthogonal directions alternatively in a super subtle way. This, of course, is extremely exaggerated. The disturbance that the gravitational waves create, which is called strain, is measured in terms of the fractional deformation. So you have a distance and then you vary this distance by a given fraction. This is what the gravitational wave causes. And the typical fractions or the typical strains we can observe are of the order of 10 to the minus 21. So 10 to the minus 21 times the original size of whatever device or reference distance you are considering. So because of this, it seems plausible to construct detectors in the following way. First of all, you're trying to observe this kind of motion in which one direction gets squeezed and the other gets stretched. So it's very reasonable to have an L-shaped detector in which you can see one arm shrinking while the other stretches. And you need a very big device because if you want to observe such a low fractional deformation, you would really like to have a very large reference distance so that this deformation is not so small in absolute terms. So that's what the LIGO detector does. And we do it in the following way. The LIGO detector has 2 arms that are orthogonal. You get a laser beams from this source, and then you have a beam splitter at some point that divides the beam in two paths, in 2 arms. The laser gets reflected at the end of these arms, in which there is a mirror, and then it creates some pattern when it's recombined. The design of the device is such as that when no gravitational wave is coming in, the 2 arms have the same length. And because of that, when the 2 laser beams recombine, they produce no signal. So this is what we call a lock. So nothing is going on, we see no signal in the output. But if a gravitational wave passes by, it's going to stretch and squeeze the arms, and the lasers are going to interact in either a constructive or destructive way, and you will see a signal pattern in the output. So this is what we actually look for, not in a single detector, but in two detectors at the time, to be able to say, or to be sure that whatever we are observing is not a local disturbance, a local motion that is changing the length of these two arms. That's something that comes from space. So that's why we have two detectors separated by 3,000 kilometers. So we expect to see the same signal in both detectors within a window consistent with the travel time between the two detectors, which is 10 milliseconds. We, of course, have a third detector in Italy that I will describe later. So just to show you what's the kind of signal we expect, I'm going to show it here in the bottom, and you see here the evolution of the system of a binary black hole. So initially, you have the two masses, or the two bodies, orbiting each other. They are approaching each other slowly, and in doing so, oops, my mistake, sorry. And in doing so, they emit a signal of slowly growing frequency and slowly growing amplitude. So that's basically letting you know that the orbit is progressively accelerating, and the gravitational field is getting stronger and stronger. So you let the system evolve, and at some point, the two masses collide with each other and are going to form a very distorted black hole that is going to emit a really strong burst of gravitational waves that I will try to freeze when it happens, more or less now. You can see here a huge amount of gravitational waves being emitted. We will discuss how much later. And you end up with a deformed black hole with the shape of, let's say, a peanut. And black holes do not like to have peanut shapes. They like to be smooth and what we call a Kerr black hole. So it settles to its final form, emitting this very characteristic emission called ring down radiation, which essentially allows you independently to tell what the mass and the spin of that final black hole is. So as I said, we detect these signals with right now 3 detectors. So we have a network of 3 detectors, 2 in the US, in Hanford and Livingston. Again, this is the one in Hanford. And we have a third detector, which is a bit smaller in Pisa in Italy, which is called Virgo. This third detector is a bit smaller and therefore a bit less sensitive. It has it has arms that have 3 kilometers, not 4, like the LIGO detectors. But this detector is quite good in detecting stuff with low frequencies. So very massive stuff, as we're going to see. This network of detectors, or rather the one formed by the 2 advanced LIGO detectors, saw for the first time a gravitational wave in 2015, GW150914. And since then, across 3 observing runs, we have so far released 50 gravitational wave events. In the future, or in the near future, we will get also we will add to our network the Japanese detector Kagra. And in 4 or 5 year time frame, I believe we will also get to join the LIGO India detector, of course, placed in India, as the name suggests. So let's have a tiny look at our first gravitational wave detector. At our first gravitational wave signal, to understand what can we learn just from observing the signal. Okay, so as I said, the typical signal we detect looks like this. You first observe a signal of slowly increasing frequency and amplitude that lets you know that there is an in-spiral process going on. So these circular orbits that slowly get smaller and smaller. At the end, you get a strong gravitational wave burst that comes from the formation of the common final horizon. So this is a distorted horizon of a final black hole. And this final black hole settles to its final shape, to a Kerr black hole that we all know, by emitting this characteristic radiation. So if you plot this in a time versus frequency domain or plot, you can see this kind of banana that we call a chirp. And that basically is letting you know again that the frequency is slowly increasing with time and the power is doing the same. So we are very good at detecting this kind of signal, especially if we have this long in spiral track, where long means 0.1 seconds, but it's long enough. So once we detect the signal, we want to try to guess what kind of system produced it. And to that, I'm going to show, I think, the only formula I'm going to show in this talk. And we basically do the following. We compared our data, which is in here, with a bunch of pre-computed templates. So we can place or we can simulate these systems in supercomputers and extract the signal we expect. Also, we can combine these results from supercomputers obtained via what we call numerical relativity with analytical solutions to obtain longer and longer signals that cover more and more in spiral cycles. And after this comparison, which we do via match filtering, we obtain a given distribution on the masses, spins, distance, orientation, sky location, and all of the parameters of these systems. So the results, when we produce them, look like this. We usually end up with these posterior probability distributions on the possible parameters of the source. In this case, this is for our first detection, and you can see that we get to the conclusion that what we were witnessing was the collision of two black holes of around 30 times the mass of the sun. Of course, one can also measure spins, distance, etc., etc. But I'm not going to focus on that for this detection. So in our two first observing runs, we observe 10, let's say, short signals or 10 typical signals from couples of black holes. And what I want you to notice is that all of them are more or less consistent with the banana or chirp shape that I showed before. So again, this lets you know that there was this inspiraling process going on. So it makes very safe and very reasonable to assume this kind of scenario. We will see in a few slides when this becomes not so safe. And on the bottom, I have a longer chirp that lets you know that the masses of this system were much, much smaller than for these ones. And this actually corresponds to the first binary neutron star that was observed in 2017. So we've done 3 observing runs, and we've released 50 gravitational wave observations. And you can see them in blue plotted in this plot. So you can see that the 2 initial black holes that we think collided. And this is the final black hole, all characterized by their masses. So just attending to the masses, we can get to the conclusion that we've seen around 47 black hole collisions, of which I'm going to highlight this for reasons that I will say in 30 or 40 seconds. We have, as I said, a neutron star merger. We have another candidate for a neutron star merger. And we have a good candidate for a mixed binary. So a neutron star merger colliding with a black hole. I'm highlighting this guy here, not only because it's the most massive of all of them, but because it has 2 very fancy characteristics if you analyze this event, which we will see in a second, under the assumption, under the typical assumption of a circular binary black hole. So you get to 2 things. First of all, this guy here has more than 100 solar masses. And that makes it the first of its kind. It's the first intermediate mass black hole that we observe. And this is quite important because to date, or until the observation of this guy, we knew of 2 kinds of black holes, the stellar mass black holes that can form from the collapse of stars, and the supermassive black holes that are in the millions of solar masses, sorry, billions of solar masses up to there, that host that hide in the center of the galaxy. So the question of how you transition from the family of stellar black holes to that one of supermassive black holes is a complete mystery. Especially if you take into account the fact that we never observed anything in the middle. So this is the first one, and we've seen that it forms through the collision of 2 black holes. So this gives good clues, or the first clues on experimental clues on how you may end up with supermassive black holes. The mass of the system is very interesting to have highly massive objects, but it's also a kind of caveat. And it's because of the following. This is a frequency versus amplitude plot for 3 different events, which are more massive as you go to the left. And the frequency of the emission is inversely proportional to the mass. So you can see here that for the least massive event of this, which is actually our first gravitational wave event, the emission from the in-spiral clearly stands out from the noise of the detector, which is this black curve. But if you start to increase the mass, you start to shift all of this thing to the left, and you start to lose the in-spiral behind the what we call the seismic wall of the detector. So this high noise corresponds basically to the seismic noise of the Earth. So you may end up in a situation where you only witness this late part of the signal, so that you would only observe the final black hole once it has formed, and just observe it relax into its final shape. So you wouldn't be able to say at all what happened to form that black hole. And that's kind of the situation we have for this event, GW190521, which is the one I highlighted before, and in which I will focus on the rest of the talk. So again, let me insist on how these time frequency maps look. Again, a typical detection looks like this. You see a clear in-spiral track here. This is again what we call a chirp, and it has, first of all, the clearly visible in-spiral track that makes you able to make some assumptions about what went on here. And this is also very, very easy to separate from background noise. We are quite good at detecting this kind of stuff. Now, if you look at GW190521, it's way more massive. So even if there is an in-spiral, you don't see it in the detector because the noise is stronger than the actual signal. And these things are very, very difficult to detect because, I mean, it's very easy for the detector to produce a signal that looks like this. You're just producing, you can think that this is essentially the signal that you get when you struck a bell with a hammer. It's a decaying exponential with constant frequencies. So there are many, many processes going on in the detector that may lead to the very similar signal. And it's very difficult to tell apart noise from signals. So that's why we only have one of these out of 50 current observations. Because, by the way, these kind of systems are also the loudest for our detectors. So when you are in this situation in which you cannot observe the pre-merger dynamics of the source, then you end up with a kind of imitation game in which you may make several assumptions about what went on there, and all of them may be right. So this is 190521 showed in the time domain. Again, you see the burst of gravitational waves, but you don't see any pre-merger emission. So could be either because it's not there, it never existed, or because despite being there, the noise is actually stronger. So if you analyze this signal under our standard paradigm of a circular merger, again, you end up with the first conclusion I said before. This is the most massive event we've seen so far, and it leads to the first intermediate mass black hole that is confidently observed. This is the total mass. The final mass is around 142 solar masses. But the second aspect that I forgot to mention is that the two colliding black holes are the most massive colliding black holes we have observed. And furthermore, the mass of this one is quite of a problem because it sits exactly between 65 and 130 solar masses, more or less. And you do not expect black holes to form from stellar collapse under those circumstances due to a process called pair instability supernova gap that makes that when you have a very massive star and it undergoes supernova, it completely disrupts the star, leaving no material behind or no core behind that can form a black hole in this mass range. So an easy conclusion to make that may solve the problem is, okay, this cannot be born from a stellar collapse, but this can be, of course, the result of a previous collision. Why not? I mean, we're witnessing this process all the time. But the story is not so easy because when the two black holes collide, the remnant gets kicked at quite high velocities that can reach thousands of kilometers per second. And such velocities can very easily eject the black holes from their host galaxies. So it requires quite a bit of a special environment to retain these kind of black holes to make this second collision possible. So the collision we actually observed. So what else can you assume about these events that may save your stellar evolution theory and science or current science? So there is a third aspect of this event that I didn't mention yet, and is that despite that we basically don't observe any pre-merger dynamics, if we assume that that pre-merger dynamics is there, we get to the conclusion that the two spins of the two black holes were highly misaligned, or with high probability they were misaligned. And this induces what's known as orbital precession. So you have this coupling between the spins and the angular momentum, and then your orbital plane starts to tilt. And this creates quite unique signatures, or can create quite unique signatures in the signal. But these signatures in such a short signal can be confused with signatures from other kind of system, which is a highly eccentric orbits. Remember, when we do our standard analysis, we assume that the mergers are circular, so there is no eccentricity. but both orbital precession and very high eccentricity can lead to very similar signals, which is what you can see here. For instance, when you compare the red signal from a very highly eccentric system, and the signal from a precessing system that is very similar to 1905-21 that can basically reproduce it. So you can confuse the red with the blue. The green line corresponds to a system with a constant orbital plane, and you can see that you actually can tell that one apart. So conclusion, you may be witnessing actually a highly eccentric system, but because you do your standard analysis, you may think, okay, this is just a circular system with orbital precession. So I'm going to go very fast, or just mention what consequences this can have for your parameter inference for what you think about the black holes. Of course, the situation of confusing many systems between themselves has to do with the total mass again. If the system is too massive, then you only see the final black hole. So as long as whatever happened before the merger leads to the same final black hole, you can confuse precession with no precession, with eccentricity. You can say anything essentially. In a regime of mass like the one of 1905-21, you can confuse precession with eccentricity, but not with the absence of eccentricity. So with a circular non-eccentric orbit, because you start to see some tiny part of the in-spiral that tells you that the system cannot be just circular and happening in 2 dimensions, so with a constant orbital plane. And of course, if the mass is too low, you have the whole in-spiral and you will never undergo or suffer this confusion. There are some consequences for the parameters you estimate on top of assuming the wrong orbit, right? So for instance, one clear consequence is that a highly eccentric merger emits very weak gravitational waves, whereas a circular merger emits powerful waves. So you need the 2 systems at different distances to produce the same wave you're observing. So one of the consequences of having a eccentric system in your data and assuming that you have a precessing one is that you're going to overestimate by a lot the distance. Overestimating the distance has the consequence that you are overestimating your redshift. So what you observe in your detector is the original signal, but redshifted by the cosmic expansion. So the total mass you infer is what we call a detector frame mass. It's a redshifted mass. But you need to correct this for the distance to obtain the true masses. So if you underestimate your redshift, you're going to end up, if you overestimate your redshift, so you make this seed big, you're going to underestimate your source mass, so your true mass for the system, and actually by amounts of 20 to 30%, depending on the source you're dealing with. So because of this wrong estimate of the mass, you may end up in a very funny situation in which you may have in reality a system that it's violating this pair instability supernova gap. So you have one of these problematic black holes, but your standard parameter inference may tell you, okay, no problem, there are no problematic black holes here, and vice versa. You may think that you're witnessing a black hole that is violating your knowledge of stellar evolution, whereas in reality, that's not the case. So some people try to look for eccentricity in the systems, including so the first one was this student at Monash University. And she said, okay, let's forget about precession and let's fold in eccentricity in the problem. But we could only achieve like very small eccentricities because of the limitations of our templates. And she got to the conclusion that the levels of eccentricity we were allowing to were not enough to describe the signal. So this posterior distribution is letting you know that the system wants more and more eccentricity, or the model would prefer to have more and more eccentricity when you compare it to your templates. The data prefers more and more eccentricity. And even if you consider eccentricity, you do not get rid of the fact that the 2 masses you infer, which are the ones in the first column, still are a problem for the pair instability supernova gap. So some of us try to go for extreme eccentricity, namely a head-on collision. And the head-on collision scenario came to our minds because essentially when you see the signal, let's say the black part, the black curve here, And you basically don't see any clear in-spiral power. We said, okay, let's consider the toy model case, which is astrophysically very unlikely that this is a head-on signal. And then if this works, then we go and explore this in more depth. The answer is that the head-on collision doesn't work for two basic reasons. The first one is that the final spin that LIGO and Virgo inferred for the final black hole, which is here in this y-axis, is quite high. It's around 0.7. And it's very difficult to form such a black hole from a head-on collision in which you do not have the contribution from the orbit to the final angular moment, to the final angular momentum, right? So one could say, okay, let's just spin up the two black holes and end up forming a very highly spinning black hole. But you have a problem when you want to spin up the black holes. That is, you're bounded by cosmic censorship. Okay, there is a limit on the spin of the black holes given by 1. So this adimensional spin equals 1. And the reason for this is that while for a Schwarzschild black hole that is not spinning, the singularity in the center is a point. As you start to spin up the black hole, this point becomes a ring. And as you spin it more and more, you may end up making the ring popping out of the event horizon of the black hole. So you may end up with a naked singularity. And that's something that scientists in general are super scared about. So we have this cosmic censorship that says, okay, we cannot have black holes with spins larger than 1. So that's a limitation on the right side of the signal. We cannot reproduce the correct final black hole. On the beginning of the signal, you can see that we are lacking with the green curve, which is the one for a head-on collision. We cannot reproduce the very early part of the signal. And the reason for this is that when you get the two black holes colliding, you automatically form a final black hole that automatically emits its rain down radiation. There is no pre-merger emission at all. And it seems that this signal actually has something. So also this tells you where this conclusion that there should be precession in the system comes from, is from this half a cycle. This half a cycle is enough to tell you that if there is an orbit and if the orbit is circular, there has to be some precession. So, and also, of course, this is not only comparing two curves. We did the Bayesian model selection on the data, and the head-on scenario is confidently discarded. So what about something else? And that's something else that we've tried is related to dark matter. So of course, we all know that dark matter is something that we know is in the universe. We see its gravitational effects, but we have essentially no idea what composes it. We have some candidates, like, of course, weakly interacting particles that may interact essentially in a gravitational way with the rest of baryonic matter. Primordial black holes are an option, and even some baryonic matter seems that can account or could account for a tiny fraction of dark matter, but not for the 27% of the whole content of the universe that it represents. So among weakly interacting particles, there is this family of particles called ultralight bosons, which I believe are the same as saying ultralight axions. And no, okay, for an axion, you need a given spin. So I'll get to axions later. And these are broadly regarded as good candidates to form dark matter. There are some searches going on within the LIGO collaboration and within the gravitational wave community, and they can be separated into two kinds. Let's call them direct and indirect. And they have to do with the fact that these ultralight bosons can form clouds around black holes, and there are some consequences. This cloud undergoes what's called a super radiant instability, and that makes the cloud unstable. So on the one hand, it makes it emit a continuous gravitational wave emission for a long time that we should be able to search with our detectors. And the second is that in doing so, they extract angular momentum from the black hole, so they spin them down. So if you start to see a population of black holes that seems to be limited by some spins that are not one, you may infer some mass ranges for these bosons. The result is that currently all results are null for this kind of technique. And this has allowed to place limits on the possible masses of these bosons and the amount of them. So there are, however, lots of kinds of ultralight bosons. There is a whole zoo, namely scalar, vector, or tensor. I believe that the vector ones are the ones that can be called axions. And the fields that make them up can be either real or complex. So each of these kind of fields leads to different physical properties, and in particular leads to different macroscopic objects that can be formed from these fields. So as I said, they can form clouds when the fields are real. When the field is complex, there can be a cloud, but the cloud is stable. So no gravitational wave emission. And they can form stars. So basically Bose-Einstein condensates of these bosons. Very funny, these stars can of course be either spinning or non-spinning, but only vector bosons can form stable spinning stars. Spinning stars made of scalar bosons or made of a scalar field are unstable against non-axisymmetric perturbations, and therefore the star would automatically implode into a black hole. So just for pictorial purposes, I have here the shape, the toroidal shape that a spinning scalar star would have, and this is the Proca-star, so the vector complex star that we are going to talk about in the next slide. So again, these Proca-stars in this case are formed of spin 1 ultralight boson fields. They do not have an event horizon, and because they do not have an event horizon or a singularity, they can have very large spins. So they are very good candidates to solve this problem with a head-on collision of compact objects that could not reproduce the right final black hole to reproduce GW 190521. And they, of course, have spins, masses. So a system of 2 colliding Proca-stars would have the same properties as a black hole merger. But there are 2 new physics parameters that single out from black holes, that are the oscillation frequency of the field, which in essence determines how compact the star is, so how similar to a black hole is, and the boson of the boson mass, or the mass of the boson that is making up the star. The mass of the boson the mass of the boson, once you know the oscillation frequency, tells you the maximal mass that star can have before imploding into a black hole. So I also want to say that the oscillation frequency is very related to the spin of the star. So the oscillation frequency determines the mass, the angular momentum over mass ratio, which is the same as saying the adimensional spin. So when one talks about varying the oscillation frequency of the star, is the same as varying the adimensional spin. So we produced a full catalog of simulations for head-on collisions of these Proca-stars. As of now, we cannot do circular collisions. And compared it to 190521. Here, for fun, you can see how the signal varies with the compactness of the stars. So you can, if you pay a lot of attention, you can see a variation essentially in the frequency of the signal, although this is very subtle, because we explore only a very few oscillation frequencies for the field. Just the range of simulations enough to reproduce this signal and see how the support or how the data would start to discard some of our simulations. So these are the 96 simulations we compared 190521 to. So the ones I have in green and red. So there is a family of equal mass and equal spin Proca-stars. We started with this super simple family, in which we just vary the oscillation frequency of the 2 fields at the time. So it's also equal oscillation frequency. And then we started to try a preliminary unequal mass model or unequal frequency model, in which the frequency of the first star is set to this value, which was the value preferred by the family of equal masses. So the results are as follows. I am showing here again the spin that was the mass and spin actually, but pay attention to the spin, which is a vertical axis, that was recovered by the LIGO and Virgo collaboration. The pink samples are those we obtained with head-on collisions of black holes, and there was this hard limit we could not surpass for the final spin. And this is what we obtained with our Proca-stars. And the darkness represents the goodness of the fit to the data. So for those that work with statistics, the likelihood that the data can be reproduced by our templates. So you can see that the darkest points are well within the contours determined by the LIGO and Virgo collaborations. Also the mass, the red-shifted mass is consistent. So, okay, we have the right final black hole, so that's very good. Another important aspect to understand what true mass for the source, not redshifted mass, we're going to infer is the distance estimate. Again, because head-on collisions are much, much weaker, we infer a distance that is 10 times closer than the one that LIGO and Virgo determined. So we get about 500 megaparsecs. So of course, our redshift is going to be almost negligible, and therefore our true source mass is going to be very different. So it was 150 solar masses for the LIGO and Virgo case for the circular black hole merger. We obtained 250, so it's 100 more solar masses in the game. Together with the distance, you always get the inclination estimate, and this is because the distance and the inclination have almost the same effect on the gravitational wave. But there is a very important aspect for head-on collisions that may help you to obtain a better estimate of the distance. And that's the fact that while typically when you study gravitational waves and all the analysis or most of the analysis that have been done to date, use the fact that the gravitational wave emission is dominated of what we call the quadrupolar GW mode, or the GW mode, or the gravitational wave mode emission that comes from the variation of the quadrupolar moment. So all of the analyses are done comparing the signals to this dominant mode. But for a head-on case, you have a second emission mode that actually is as dominant as this one, and their distribution on the sky of the source is different. So if you are on the top of the source, you will only observe this quadruple mode, whereas if you start to go to more equatorial positions, you start to see the contribution from the secondary mode. So that tells you that helps you to decide whether you are on top of the orbital plane or on the edge. And that helps you also to constrain the distance. So the blue contours here in terms of inclination and distance correspond to our estimates with the two modes in our analysis. So 0 corresponds to being on the top of the system, so on the direction of the final spin. Pi, of course, you are on the bottom, and pi over 2, you are on the orbital plane. So we obtain this estimate. If we remove this mode from the emission, then we cannot identify so well the inclination, and we get a broader estimate. Now, a parameter that is never reported for any gravitational wave emission is not whether you are on top or the bottom, let's say the inclination angle with respect to the source, but the azimuth angle, so where you are around it. And this is essentially because when you have a circular merger, there is no clear way of defining a preferred direction in the orbital plane. But if you have a head-on collision, there is a very, very well-defined axis, that is the collision axis. And you can define an angle with respect to the collision angle, to respect to the collision axis. So you can try to say where you are around it, or what's the projection of your location on the sky onto the orbital plane. So we did that. And when we include this 2-0 mode in the emission, which also creates some asymmetry in the emission, you get to the conclusion that if this is a head-on collision of two boson stars, then you are either on the first quadrant or the third quadrant of the plane defined by the collision. So you are able to measure this because of frame dragging. So the two stars are spinning, and the spin of the stars makes the trajectory not straight, but they curve a bit before colliding. And so what you're really saying here is that whatever location you have, the star that is closer to you has a trajectory that actually approaches to you as it curves. So that's the measurement you're really making. And as far as I know, this is the first time that frame dragging effects can be observed in a gravitational wave. And of course, under this super restrictive scenario of a head-on collision. So on top of reading properties assuming a given scenario, you need to say, okay, whether your new scenario is statistically preferred to the typical LIGO-Virgo scenario of a black hole collision. So we performed a very detailed Bayesian inference study. And the result of that inference study, or model selection study, sorry, has two main ingredients. First of all, how well your model can fit the data. So the better the fit, the more statistically preferred the model will be, but also the size of your model. If you're exploring too many options to achieve that good fit, your model is going to be penalized, what we call the Occam penalty, which is also called in some other places the look elsewhere effect. So the fit to the data is given by this number in terms of log likelihood. So basically, you can see that the head-on Proca-stars offer a slightly better fit to the data, which is not enough to claim any statistically any strong preference for this scenario. And when you perform the full Bayesian inference analysis, you can compute the log evidence, so the logarithm of the evidence. And you can see that these two numbers are larger than the one we get for black holes, and are much larger for the head-on collision of black holes. So how much larger are, you need to, is read in the following way. So for instance, in order to know how much more probable this third model is with respect to the head-on collision of two black holes, you just get the exponential of the difference between these two numbers, okay? So if you do that with respect to the black hole case, to the circular black hole case, you end up in the conclusion that the Proca-star model is between 2 and 7 times more likely than the black hole case. So that's statistically not very significant. This is just this just proves that the two scenarios are degenerate, and that it's very promising to keep exploring this. Now, there is a thing I would like to note here, and is that, of course, when you do this kind of analysis, you impose some prior knowledge or some prior assumptions on what the sources look like. So one very reasonable assumption to make is that sources distribute uniformly in space. So the farther you go away in your sky sphere, the more sources you're going to find. So the farther away the source is, the more likely it's going to be. Now, remember that circular black hole mergers are much louder than head-on collisions. So that means you can place them much farther away. And therefore, there's going to be like an intrinsic bias for the circular binary black hole case. So if we eliminate this prior from the game, we can compute new evidences, and then your evidence, let's say just on how well the data is reproduced and how big the parameter space is, but not how loud the signals or the sources are, returns you probabilities of 30 to 1 and 70 to 1, which is way more significant, although of course not enough to claim anything. So this analysis is of course physically a bit irrelevant, but it tells you that you should work on obtaining simulations for circular Proca-stars, for circular mergers, because then you would be able to place them very far away and probably recover these numbers that we show here. So just to finish with, what about the new physics? So what about the oscillation frequency of the field? Can we measure it? And yes, we can. We obtain this value of more or less 0.89. And well, the fact that the posterior distribution is dying tells you that we explored a big enough parameter space to claim some conclusions. Now, this oscillation frequency on its own is a bit meaningless if you do not combine it with the total mass of the star. Combining those two lets you know the mass of the ultralight boson that should be there. And we obtain something like 9 times 10 to the minus 13 electron volts, which is, if I am doing my math correctly, billions, American billions of times smaller than the electron. So this is the mass we get. With all of this data, you can actually determine what's the maximum mass that such a star formed by this kind of ultralight boson can have before imploding into a black hole. And this actually helps you to determine whether other LIGO events could be consistent with a head-on collision of Proca-stars made of this kind of bosons. Because if you do not reach at the end of the process this mass, then you're not going to witness the ring down of the final black hole, and therefore you're not going to mimic the signals that LIGO is observing. So this kind of mass basically rules out any other event as a Proca-star merger. But be careful, because this is under the very restricting scenario of a head-on collision, which limits a lot the boson mass range that we obtain. There is a very funny story here, is that the boson mass that we obtain is consistent with all of the limits that have been placed via the studies I mentioned about boson clouds. But you cannot compare them, because these clouds are only unstable and emit gravitational waves if the bosonic field is real. But we are working with complex fields. So there is no GW emission, no spin down. Anyway, the bosons are different, so you cannot compare those two numbers. I don't know why this slide is here. And just to finish with, we are now extending this study to a larger catalog of simulations. This is why I had all of these simulations in the previous plot. This is the initial study with this limited set. And what I can tell you as of now is that despite the fact that the evidence for the Proca-star model does not increase significantly, it's basically nothing, the fit to the data itself improves a lot. So that means that if you were able to produce against circular collisions with whatever couple of stars is colliding here, I believe this number is going to increase significantly. So 2 last slides, but in the future. So feature number 1, we need to detect more high mass signals to be able to fit them with these head-on collisions, which is what we can do right now. So you have 2 options, either signals like GW190521, which are very difficult to detect, but we expect more just because LIGO and Virgo have detected already 1 and they are going to get more sensitive. But there is a family of signals from high mass systems that you should be able to tell apart from the noise, and you should be able to distinguish, to detect very clearly, which are the signals you observe when you are in the orbital plane of the system and you have these extra gravitational wave harmonics that are going to give you this super rich structure that my personal belief is that you should be able to separate from the noise. So we are working on this quite heavily. And I can tell you now that we have a search ready, almost ready to look for these kind of signals. And it's way more sensitive to these kind of signals than current searches. And the second thing is that if you want to conclusively determine whether Proca-stars exist or not, you have 2 options. The first one is to detect more events like the one I discussed and build tiny evidences across many events. Or you want to observe a collision of Proca-stars in which you form a hypermassive Proca-star in the process that survives for long enough before colliding into a black hole. So it emits this characteristic emission that black holes cannot reproduce. So we're also planning to do a targeted search for this kind of system. So this is the end. These are my conclusions. Sorry if I got a bit over the scheduled time. So just want to go very shortly over the first part of the conclusions because I didn't really cover them in the talk. So in general, not only Proca-stars, but observing very heavy compact binary mergers is very tough, but it's extremely rewarding because of 3 reasons. Basically, you can observe gravity in full detail because the emission is very strong in the detector, the emission that happens when the 2 black holes collide. And you can observe this whole family of harmonics, so that can allow you to test things like the no-hair theorem, the behavior of dynamical horizons, recoil velocities, and all of this. Of course, they are going to pose potentially challenges to stellar evolution, like identifying black holes or potential black holes in this pair instability supernova gap. And as I said, the gate for boson stars or alternative scenarios is actually open because you cannot tell anything about what happened before the collision. So the new observing run is going to commence in 2022 with much more sensitivity especially to these heavy objects. So let's stay tuned, and that's it. I will take any questions if you have them. Thank you.
Okay, thanks a lot. That was for this very engaging talk. I liked it very much. Let's see, I have a couple of questions, but of course I'll have to let the audience first have their turn. So if anyone has questions, please just speak up. And otherwise, let me see if there's any raised hands. In the meantime, let me, as people think about it, let me ask first one. So when you're considering the, when you're sort of computing the evidence, the Bayesian evidence of different scenarios, one of the things that you talk about is the computation of the prior in terms of what are the sensitivity of the detector, etc. But there's also, I would assume that there should be also an astrophysical prior, right? Let's say telling you, what is the actual probability of 2. I mean, I'm imagining, 2 stars just having a head-on collision. I mean, of course, you commented this, that you need simulations of other kinds of events, but just I'm not sure if the fact that you only can simulate this becomes a little bit more of an academic exercise of, if this had happened, this is the sort of signal that would be seen and is compatible with my results. But really the astrophysical prior for that to actually happen, I'm not sure how much it is.
It's essentially zero. There are recent studies that have demonstrated that very highly eccentric collisions can actually happen in some kind of environments with more probability than we thought. But in any case, I completely agree with you. You can't even label this as an academic exercise, but the philosophy here is the following. You have models for black holes that have been evolved or developed for 15, 20, 30 years. And those can, and there is a toy model you can construct with Proca-stars that actually beats them in fitting this signal. That's on the one hand. Of course, the astrophysical scenario you're considering has zero probability. But once you are able to develop circular mergers, the expectation is that you should be able to reproduce a signal exactly like this one. Just reducing a bit the spin of the stars and letting the orbit actually contribute to the final spin. And also, because those signals would be actually louder, you would be able to place those systems farther away, and this evidence is going to increase. So this is a demonstration, essentially, that pursuing those simulations should be done.
Yeah, fair enough. And what is the, now that you mentioned it, what is the limitation for that kind of, is it on the theoretical side, or numerically the computations are really outside of
it's
the
more on the
it's
more on the numerics. So in order to perform these simulations, you need to prescribe an initial conditions for the system that you want to evolve, namely initial data or initial space-time foliation. And for that, you need to set up the initial geometry of space-time when the two stars are far apart. So for the case of a head-on collision, you can just prescribe such a space-time as the superposition of the two independent spacetimes of the two stars. The problem is that this violates Einstein's constraints equations. So you're starting with an initially violating or not realistic space-time that then converges to something that actually satisfies those conditions. And then you would have to do a recursive method to end up finding a initial space-time that you can trust. Okay, and so you can trust the whole simulation. This process can be done for circular mergers, but it's more of a technical issue. You need to allow these codes now to eat numerical initial spacetimes, not analytical as we do with the head-on collision, just because of how complicated it is to solve the equations. And the second is you need to get rid of some simplifications like symmetry around the orbital plane. Sorry, not the orbital plane, but axis symmetry and all of this. So we are now starting to get them.
Okay. So I see it's like a software part in which it's really not prepared to get some specific inputs. And then there's also a bit of a theoretical part in which some sort of symmetries are assumed and that have to be developed.
Yes. As you can imagine, the conceptual underlying problem is not there because we can do this for black holes. So we know how to prescribe these space times that have compact objects in a circular merger, and we know how to simulate them. It's just the technical, or this, if you want even to boil it down, the software issue of just modifying everything, make sure it works, etc., etc.
Okay, great. Okay, so it seems solvable, like people working on it rather than, I was thinking whether it meant, very large computational resources. That it's different when you have to ask for, two people.
Okay, that's the third issue. I always overlook. The circular orbits take way more time than the head-on collision. Okay. So if you want to be efficient in producing them, you need a significantly larger computing power.
I see. Okay, any questions from the audience? Are there, another one for me then, are there any other signals that people developing this or that have proposed Proca-stars? I mean, in terms of interaction with other astrophysical objects, or any other, besides, of course, the usual dark matter evidence, is there any other way that we might infer the existence of this kind of objects besides the gravitational?
Okay. So I'm being a bit bold here, but the people that actually came up with these Proca-stars recently showed that depending on the angle of observation of supermassive black holes, or putative supermassive black holes, then the event horizon telescope-like picture that you get, you cannot distinguish it from that of a Proca-star. If you look from certain angles, if you look essentially from the accretion disk, let's call it the orbital plane, then you can tell them apart. But for a system like M82, you cannot. So I guess that once those observations get very, very sensitive, you may be able to resolve the gravitational effects around the star or the black hole that whatever compact object is there is creating on the surrounding matter. But that's the only thing I can think of right now, because these Proca-stars, sorry, these ultralight bosons, this particular family is not going to create it's not going to emit these gravitational waves that they emit when the clouds form around black holes. So I cannot think of any other way to observe either this particular ultralight boson field or the Proca-star in any other way.
Mm-hmm. Yes, I was thinking sort of electromagnetic signature of any kind, but I'm not sure.
I tend to think they can have magnetic fields, though. So maybe, I don't know.
Okay. All right. So I don't see any raised hands. Last chance for questions. Okay, Juan, again, thanks very much for this very interesting talk. So this probably will be made public at some point, if you don't mind, maybe on the YouTube channel. Okay. So thank you, and thank
you very much
for participating.